Many astronomers are really driven by the search for Earth twins because I think deep down the natural endpoint of this whole goal of looking for planets is to answer the question, are we alone? That is a burning itch that I think many of us have our entire lives wanted to answer. I'm sure many of you feel the same way as well. So I think that was what really drives us. But whenever you have a temptation, a goal, an aspiration that you're reaching for, it is so easy to get blindsided and drawn into dark avenues that aren't really true, especially in science. That can happen quite often. And so we've already had several claims of not only Earth-like planets, but even life. There's been claims of life on Venus, there's been claims of life on interstellar asteroids, and of course there's many UFOs that we often hear about. So there is a natural temptation to look at anything that seems anomalous, that seems a little bit different, and immediately reach for aliens. Because of course, deep down, I think a lot of us really want that to be the answer, that we are not alone. This drives us, it inspires us, but it's always a risk that we could go too far into that temptation and see aliens where there's none really there, and we have fallen prey to that trap many times in the past.
The search for alien life.
One of the primary tools that astronomers use to think about the abundance of life in the universe is the famous Drake equation, first written down by Frank Drake. It is essentially the number of stars in the galaxy multiplied by a long list of possible factors, such as how often do you have planets, how often are those planets Earth-like, how often does life begin on those planets, and so on and so on. Now, when we look at this, it's like a narrowing filter, and you can imagine with the rare Earth hypothesis adding on extra terms, such as having how often does the planet have a large moon? How often does it have the same mass as the Earth? How often does it have the same land mass fraction the Earth has, or the same ocean salinity or chemistry, etc., etc.? And you can imagine adding on hundreds, even thousands of extra parameters onto the Drake equation, which get ever narrower. And of course, if you multiply a very large number of fractions together, you'll eventually get zero. And I think this is one of my big problems with the rare Earth hypothesis, is that it's a very narrow view of how life began and how life must survive on other planets. All of these factors have to be true. It is a singular path. And that is a path which has indeed led to success, but perhaps there are different paths parallel to us, which are completely different, yet also lead to life. And so the Drake equation simply multiplies fractions by each other, but perhaps truly what it is missing is an additive sign. There is a second path below it, a different way of getting to intelligent civilization, and a different way after that, and a different way after that. And so perhaps not only should we be multiplying all those things, but also adding up all those parallel tracks. And it is that addition that we just really can't do without a lot of creativity and discovery, because right now we only have this sole example to look at. What is life though? What are astronomers actually ultimately hoping to detect? Defining life is an incredibly difficult task, and there is definitely no consensus about how to call such a thing. Maybe it's actually better to call it more like porn, like you will know it when you see it, rather than having a strict textbook definition of it. NASA have certainly tried to have a definition. For a long time we had a definition from NASA that said it is a self-replicating chemical system capable of Darwinian evolution. And that's pretty good, but maybe chemistry isn't actually necessary. Maybe you could have an AI system or self-replicating technology that would still resemble life in many ways, but wouldn't actually involve the kind of chemical systems that we're familiar with. So whenever you come up with one of these definitions, it's really easy to poke holes in it and say, well, what about this? What about this? And I think it's just too hard for us to come up with a singular thing to say this is exclusively what life is until we've discovered more examples of it. That's the quest that we're on. We're going to look out, we're going to try and find examples of things which resemble properties of what life does, and then we'll do the hard work of truly trying to classify what actually is life in the first place and where do we draw our boundaries. The necessary conditions for life on a planet are still up for debate as well. We really don't know exactly where the limits of life are. When we look at life on Earth, there are some organisms, especially extremophiles, that can cope with fairly large ranges of conditions. So for example, there's some thermophiles that can range from minus 25 degrees Celsius, and then you have other extremophiles which can live at 125 degrees Celsius. So 150 degrees Celsius range of diversity. But the fact that extremophiles today can survive in such an extreme range of temperatures doesn't mean that life could begin under such an extreme range of temperatures. Maybe the nascent conditions for the birth pangs of life to begin with, the abiogenesis event, the spark of life which created all life on the Earth, maybe that requires very special and subtle temperature range that cannot be violated. And perhaps things as cold as minus 25 degrees Celsius are just way outside of that range. These are questions we just don't know. What were the initial conditions on the Earth that led to the emergence of life? Similarly, we can't assume that just because extremophiles on Earth can only survive from minus 25 to plus 125, that means that life elsewhere could not survive under even more extreme conditions, because it could be based, of course, on different chemistry and use different thermodynamic rules than the ones that our life currently uses. So there's a lot we don't know. But I think the idea of just narrowing in on the places where liquid water could survive, which is from 0 to 100 degrees Celsius, that certainly makes a lot of sense, because even those extremophiles still require liquid water at some part in their life cycle in order to survive. So I would be comfortable with that as an initial hunting ground, with the idea that we might perhaps extend that to more diverse environments as we go on. The Copernican principle, named after Nicholas Copernicus, also goes by the name of the mediocrity principle, and sometimes in cosmology is an extension of it called the cosmological principle. And all of these ideas essentially say the same thing, and that's that where we are, where we live, even when we live, is typical. Everything about us is normal, and therefore we should expect that if we go to another part of the universe, it would look basically the same as it does here. And usually this is a pretty good argument. Take, for example, the instance of Neptune. We have a Neptune, in fact, really two Neptunes in our solar system, Uranus and Neptune, and they don't seem to really play any part in our own evolution out there in the distant part of the solar system. And so you might reason if we have two of them, perhaps other solar systems should have them too, by this mediocrity principle, the idea that we are typical and normal. And indeed, that would be strikingly true. When you look out at these exoplanets, that's what we find. We find Neptunes all over the place. They are indeed a very common type of planet. But here's where it runs into problems. Let's imagine we use the Copernican principle to argue that the Earth has an oxygen-rich atmosphere. Therefore, all of the planets in the solar system should have an oxygen-rich atmosphere or liquid water, whatever you want to choose. And of course, many features of the Earth are incredibly unique and special to the Earth itself and are not found on any of the solar system planets, and perhaps not found elsewhere in the universe too. We just don't know. And there's a good reason for that, and it's called the weak anthropic principle. And the weak anthropic principle basically points out that you can only live in a place where conditions are suitable for you to live. So it's not surprising that we don't live on Pluto. It's not surprising that we don't live on a moon of Neptune, because those places are so cold, they have very little atmosphere, that of course a human being could never have evolved on such a world. We would of course live on only the subset of exoplanets, or planets in general, where the conditions were right for life. And those conditions themselves could be very, very rare. Maybe there is only 3 Earth-like planets in the entire universe, as far as we know. It should not be surprising that we find ourselves living on one of those 3 Earth-like exoplanets, because perhaps that is the only place where we could live, and all the other places are just simply devoid of life. So when we use the Copernican principle, my big caveat would be, look, it's okay to use it when it has nothing to do with our survival, our emergence. Neptune, fine. Neptune has nothing to do with why we're here. There's no way which Neptune affects life on this planet. But the moment you use it in a case which is connected to our existence, which is predicated upon our existence, such as maybe the presence of a large moon or oceans on our planet, then we have to be very careful. I don't think in those cases we can reliably use the Copernican principle, because if we do in the solar system, it clearly fails. So in that case, I think we should just take a beat and really analyze how connected we are to the statements that we are making. And that's why I do not buy the argument that by the Copernican principle, life must be common. It is kind of a circular statement, I would claim, to make that argument. One way that we have attempted to classify hypothetical alien civilizations is with the so-called Kardashev scale. So the Kardashev scale basically splits civilizations up by energy usage. And maybe that's a somewhat archaic way of thinking about it. Today, I think maybe we might think about capabilities more than energy usage, but this has still remained a very persistent way in which astronomers think about how we might split up civilizations. So a Kardashev type 1 civilization is defined as a civilization which uses all of the energy which is incident upon its planet. And we are not there yet. We do not have our planet covered in solar panels and use that amount of energy. That still greatly exceeds our current global energy consumption. A type 2 civilization would be one which not only uses all the energy on the planet, but uses all the energy of the star. So you might imagine a type 1 civilization being able to control their weather and their climate, but a type 2 would be able to control the entire solar system, be able to move planets and moons around at will as they needed. And practically speaking, in order to harvest all the energy of a star, you'd probably need to build some kind of giant shell around that star, often called a Dyson sphere, after Freeman Dyson, who first proposed that idea. And that shell, or swarm of material, would absorb all of that starlight, which you could use for whatever you want to do, computation, manufacturing, whatever advanced purposes these civilizations might have for such an energy need. And if you just go another step further, you can do it to Kardashev type 3, and that's one that not only controls their solar system and all of the energy output of their solar system, but now goes to the entire galaxy. I think most realistically, you might imagine a civilization like that living around Sagittarius A star. That's the supermassive black hole that lives right in the center of our galaxy. And that thing spews out gigantic amounts of energy that you might imagine a very advanced civilization harvesting and using. And indeed, I think it's an interesting place that we should consider looking for alien civilizations. Maybe not an intuitive place, but a place that I think we have a good argument as to why they might end up in the center of a galaxy. Hart's fact A, named after Michael Hart, is connected to the Fermi paradox, the idea as to how come we don't see aliens out there if it seems like they should be out there. And fact A in particular points out that there are no aliens on Earth right now. We don't see a civilization cohabiting the Earth with us. We haven't been totally colonized by an alien civilization. It appears to be a very lonely planet with just one civilization, which is us, living on it right now. What I like about fact A is it's kind of indisputable. It's one of the hardest points we can really say in astronomy. I can't claim that a distant exoplanet doesn't have an extraterrestrial civilization on it, but I can be much more assured about the fact that we are not currently cohabiting the Earth with another alien civilization. I feel much more confident making that claim. And even that claim, as weak as that might seem, does put some interesting limits upon the behavior of other civilizations. It means, really, that a galactic civilization does not exist, that there is no instances of a marauding berserker type civilization that just decided to gobble up every exoplanet, every real estate it could find, and turn it into another colony for itself. Because if that had happened, the whole Milky Way would have been colonized by now and we wouldn't be here. This really connects to the ideas of self-replicating probes, also called von Neumann probes, which have been argued for a long time to be a real problem for those thinking about life in the universe, and especially life in the galaxy. For it turns out that even though the galaxy is very large, 100,000 light years across, even traveling the galaxy at sort of Voyager 1, Voyager 2 type speeds, the speeds of our current spacecraft, it should have been eminently possible to have colonized the entire galaxy many times over during its 13 billion year history. That's a long period of time for all of that colonization to have taken place, and you really don't need to have fast rockets to have colonized the entire galaxy by now. Yet clearly, that hasn't happened, as fact A demonstrates. And so that's interesting. It means that maybe civilizations do emerge elsewhere in the galaxy, but they never have the will or the capabilities to conduct such an expansion phase, such an aggressive expansion phase where they take over the entire galaxy, because of course we wouldn't be here had that had happened. That is probably one of the strongest data points I think we have. We don't have any evidence for life outside of the solar system. And so when we talk about the propensity of planets to form life, probably the only strong data point we have is the fact that we're here, but also, more importantly, when life appears to have emerged on the Earth. And strikingly, it appears to have emerged very, very quickly in the Earth's history. Now, this naively could be taken to say, well, therefore, if life starts quickly, it must be an easy process. But we have to be careful when making such claims. Perhaps the evolutionary process to go from the simplest forms of life to something like us, a self-aware entity which can do all of this paleontology, all the statistics and math, maybe that timescale takes 4 billion years pretty much all the time on these types of planets. And if it consistently takes 4 billion years for that process to play out, life kind of has to get going pretty quickly, else there wouldn't be enough time for us to have emerged in the first place. I think a surprising fact about the Earth people don't realize is that it will likely become uninhabitable to complex life in less than 1 billion years' time. And so life really does have to get going quickly, else there just wouldn't be enough time in that evolutionary process to get to us. So we could naively look at that early start to life and say, therefore life is easy. We add this complexity of evolution, say, maybe not so quickly. But eventually, if we push that early start to life further and further back, you eventually overwhelm even that evolutionary timescale, and you do end up with a genuine result that actually there's no way around it. Life actually is an easy process, despite all of the nuance of that evolutionary argument. And indeed, I think for the first time, we are seeing signs that we are crossing that threshold. There was a recent result that we are able to date the emergence of life on the Earth to 4.2 billion years ago. And for context, the oceans formed 4.4 billion years ago. So within 200 million years, really a cosmic snapshot, we had the conditions ready for life emerging, and we went all the way from there to the first organisms on our planet within 200 million years. That is such a short period of time that it overwhelms that evolutionary argument, and you have, for the first time, I would claim, strong evidence, not definitive evidence, but strong evidence that life is indeed an easy process to get going, at least under the conditions that the Earth enjoyed. So based off the early start to life on the Earth, we might genuinely think that simple microbial life could be quite common, at least assuming that Earth-like conditions are common in the universe. So we'd have lots of planets out there with simple life on it. Now the interesting question then is, how often do those simple life forms develop and evolve all the way up to something that is like us? Here it took 4 billion years, perhaps it takes a little bit less or a little bit longer on other planets. And so we might look forward to the future and say, if it takes 4 billion years for this process to happen, surely as the universe ages, there should be an emergence of more and more civilizations into the future. But we actually have to be a little bit careful with that argument too, because stars and planets have finite lifetimes. They don't last forever. They eventually die. Our own Earth will die as a habitable biosphere in less than 1 billion years due to the evolution of our star. As the star evolves, it grows in luminosity and will actually eventually make the Earth too warm for liquid water and thus life on our planet. So there will be a collapse point in less than 1 billion years when that happens. So this sets a time constraint for life in the universe. Not only do you have to have life get going fairly quickly, then you also have to have enough time for that evolutionary process to play out and get to something like us. And this immediately rules out a large swath of stars as possible places where a civilization might live. For example, stars which are more massive than the Sun have shorter lifetimes. They burn through their nuclear fuel much faster. And so perhaps those stars wouldn't have enough time for a civilization to develop on them. Vice versa, we have the M-dwarf stars, stars which can last for trillions of years in some cases. And so potentially that might be the place that in the far future, we can imagine civilizations emerging, and we would be the first, the weirdos of the universe who lived around a sun-like star early in its history, and civilizations emerge much later on around these M-dwarf stars. There are two basic strategies which we might attempt to search for life in the universe. One is with a so-called biosignature, that is a signature of biochemistry essentially on another planet, and a second is a technosignature, the signature of technology. Now technology obviously requires that not only do you have life, that an advanced civilization also developed on those planets. And so that naturally seems like a smaller piece of the pie to look at. However, those technosignatures could be very, very loud, heard from millions of light years away potentially, and could also perhaps be very persistent. We can imagine a civilization maybe building a beacon or something that could last for billions of years to perpetuate its knowledge into the cosmos. So a simple balance is not so easy in weighing which of these options would be most fruitful. The biosignature case certainly has had, I'd say, greater attention from entities like NASA and government funding agencies, because after all, you don't require all this evolutionary complexity. You can just have simple life and potentially still be able to see them. The way biosignatures work is to look for gases that are emitted into the atmosphere, which are uniquely produced by life. At least that's the theory. The problem is, it's very difficult to find gases which are indeed uniquely produced by life. Lots of gases can be produced through geological processes as a side product, and so that can become a false positive to our search efforts. A classic example of this is oxygen. Of course, plant-based life manufactures oxygen on the Earth through the process of photosynthesis, and so it would seem like oxygen would be a good thing to look for, especially because oxygen is a very reactive molecule that really doesn't want to hang around in an atmosphere. Something has to be making it, because otherwise it just reacts with stuff and oxidizes and so quickly disappears. The fact that our planet has a sustained level of oxygen proves essentially that life is here. At least that's true on the Earth. But we could imagine different types of planets where oxygen is being manufactured without the need for life at all. One possible way this could happen is through a process called photolysis. So ultraviolet radiation from the sun strikes the upper atmosphere. And if there is water in that atmosphere, H2O, the H2O will be split up into the hydrogen and the oxygen separately. Now, hydrogen is very, very light. It's the lightest element you can have, and so it's very easy for it to escape into space and simply be lost, like letting go of a helium balloon that disappears into the sky. But the oxygen is heavier and it sinks, and so you can end up with just ultraviolet radiation plus water in the atmosphere generating a significant amount of oxygen in a planet without any life involved. And so that signature would be a false positive for us. If we're not careful, we would interpret that to be life, whereas in fact, it is not. And so astronomers, chemists, biologists, we're involved in this game now of trying to imagine all of the different signatures that life could produce and all of the different confounding factors that might trick us, and trying to find those unique combinations that we really trust as being the smoking gun that this has to be life. So it's a very complex chemical field that we're involved in, but ultimately a tractable question, but a question that we still need to work really hard on. From a scientific perspective, the question we really care about is looking for life on these exoplanets, and indeed planets in the solar system as well. So for example, Mars is a good case study. We have sent robots there which have attempted to look for life, and a big question has always been, are we accidentally carrying life with us to that planet? And thus, when we do the experiment to look for life, are we maybe accidentally detecting just life which hitchhiked a ride and joined us on that journey and arrived at Mars without really that being the intention? It's actually very, very difficult to totally sterilize a spacecraft and eradicate every single spore on the surface of that thing. There is essentially always going to be a little passenger which hitches a ride with you. But we of course want to minimize that as much as possible to reduce the chance of that being a false positive. And so this raises some interesting ideas about where is the best place to look for life, because Mars has had a lot of contamination, not only from spacecraft from the Earth, but also asteroids. Even before we had a space program, there was still material being constantly swapped between the Earth and Mars just by meteorites being knocked off one and landing on the other. So perhaps life has long contaminated Mars even before humans were around. But there are places in the solar system where that shouldn't have happened. You look at the icy moons of Europa and Enceladus, for example. Those are protected by a thick ice shell, many kilometers thick, which should really prevent any material being able to penetrate through that ice and get into that subsurface ocean. So for me, I think those are the most interesting places to look. We could drill down through, hopefully be very careful about contamination, and we would have a pristine location where if we detected life there, I think we could be pretty assured that was not a contamination from the Earth. This was a genuine second abiogenesis event. And once you have two starts to life in the solar system, that would essentially establish that life really would be everywhere in the universe. I think we have to accept the possibility that even though we're on this quest to look for life in the universe, we may never get a conclusive answer either way. I certainly hope that we can find an answer, but it is possible we never will. For the truth is that space is just a very, very huge expanse to try and explore and have conclusive answers on. One of the hardest scientific aspects of this is that you can't prove a negative. So I can never prove to you that Mars does not have life on it. I can look at the surface and claim on the surface I am 99% sure there are no microbes. But then you could also say, well, what about underneath the surface? Have you checked there? What about underneath that rock over there? Or behind that canyon or behind that hill? And so I can never totally prove, even on the nearest planet to us, Mars, that it does not have life on it. So what hope is there in that sense of ever proving that we are alone? It's impossible to prove we are alone. We will always wonder about that. We can get a series of null results, of negative results, but it's never going to establish true loneliness. The fact that space is simply so large means this is a challenge that maybe we should be patient. I mean, I hope we can get an answer in my lifetime. I would love to know the answer in my lifetime. But this may be a journey that humanity undertakes over not just centuries, but maybe millennia into the future, in a similar way that Galileo 400 years ago was first starting astronomy and couldn't have imagined how astronomy and the discovery of exoplanets and cosmology would be born from his creation of the telescope. We have a long journey ahead of us in astronomy too to answering this question about life in the universe. But it is the great question, and a question which I think many of our future descendants will be inspired to continue studying.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.